Hello all. In this video I'm going to go over the basics of what a decision tree is, and we'll think about how we're going to go from a spreadsheet, a table of data that is our data set, into constructing something that is a decision tree. So how do the pieces of the data in the data set map onto the parts of the decision tree? So here I have a kind of a not very beautiful example of a decision tree, but it does capture the essence of it. When you have a decision tree, it's a tree data structure, and the interior nodes of the tree all ask questions. And then the different possible answers each become a branch of the tree. So here at the root of this tree, we have the root node asks about color. And this is the dog example that I've mentioned in the earlier video. So we're thinking about dogs. We have certain attributes. This is a very, very small toy example. The dogs have color, they have a fur type, they have a size, and they have a personality, which is a really bad category to have, but just go with it. It's a toy example. So the top of the tree, the first question we ask about a dog is, what color is this dog? And we have four possible categories there, very simplified from what reality is: brown, black, white, and gray. Each of those goes to its own decision tree, where you might ask additional questions. So here you see if the dog is brown, we're going to go over in this direction. We'll ask what size the dog is. If the dog is black, we'll go and ask about personality. If the dog is white, we'll go on to ask about fur type. And if the dog is gray, we go to a leaf. So the leaves on the trees represent the categories. And those categories in this case are either yes or no. This is the good dog category. So someone's looking for a dog that they want to adopt, perhaps, and we want to know whether or not any particular dog is a good fit for them or not. In this case, if the dog is gray, we don't need to ask any further questions. This person has said they do not want a gray dog. So the answer is no. Notice that in different branches of the tree, different subtrees, the same question can come up at different points. So over here we have fur type being a question that's asked, and on the left subtree it is asked, but only after we ask size. So the same questions can occur in different branches of the tree. In fact, they usually do, but if you walk any path from the root down to the leaves, you'll never see the same question asked twice, because it wouldn't make any sense. Once we have asked about color here, when we're in a particular subtree, we know the color of the dog. We've already assessed that. So this is only questions about brown dogs. And this one right here, we only ask these questions of black dogs, and so forth. So you can see we have other questions that get asked, and then eventually we hit leaves. We have leaves that are yes, we have leaves that are no. There are also these pink leaves. This is a very small data set when you actually start working with it. And it turns out that there are some categories, some sets of features we don't even have data for. So in this case, if we look at brown and then follow this link here to small brown dogs, we do not have any examples in the data set, because otherwise we would have something here, either another question to be asked or a leaf node. And the same for black dogs with a nice personality or black dogs with a mean personality. We just don't have any examples in the data set. So a lack of data is something you might have to handle when you write an algorithm to build one of these decision trees. So building the decision tree is what the machine learning algorithm does. This is the model that's trying to capture the patterns in a way that works and that is generalizable. So we say that a decision tree is consistent with a given data set if you take every instance in the data set and you walk through the tree and you get to a leaf node that matches its category. It's inconsistent with the data set if there is some miscategorization that happens in this tree. So the very baseline we want from a decision tree is we want it to be correct on the data set that it's been given. We don't want it to give incorrect answers. We, of course, as machine learning people, we want it to generalize beyond the data set it's been trained on, and that's where things really get interesting in how you choose to build the decision tree. Because there are, for any data set of any reasonable size, potentially hundreds or thousands of different trees you could build. And so the question then becomes, what is it we want out of these trees? And how can we write an algorithm to build better trees that'll help it to generalize better and that will help it to be efficient to use? We don't want big sprawly trees. We want something that is compact. But what that means is different than, say, what we might do if we were talking about expression trees or binary search trees or other sorts of data structure kind of questions. This is a very specific kind of tree, and it turns out that what we want from that tree can look different than some other trees you may have studied. All right, so the algorithms need to pick good questions to ask first. They want those questions to discriminate among the data as much as possible so that we have the least number of additional questions to ask as we go down the line. One of the really great advantages of decision tree learning, it tends to work really pretty well. It's a very popular kind of approach. But beyond just working well, one of the big advantages that decision trees have is that it's an artifact you can actually look at. You can look at this tree, you can unpack it, and you can see why the algorithm makes the decisions that it makes. So you can tell from just looking at the tree that, oh, all gray dogs are going to be no. That's why it says no when you offer up a gray dog. You can see that it's really only paying attention to personality among black dogs and not really paying attention to anything else. So it fits within the realm of explainable machine learning. The decisions are not opaque, unlike neural networks, where it's very unclear why it's making the decisions that it's making. The decisions are something you can actually see. And that's a big advantage for decision trees over other models. All right, there's one other thing that I want to talk about here, and then I think what we'll do is pause, and in the next video we'll get into the details of a specific decision tree builder. I want to point out some of these resonances, that is what I think of them as. That there are the same ideas coming up in different places, and we have different terminology that it's all kind of talking about the same thing. So when we think about a decision tree, we think of the interior nodes as asking questions, and the leaf nodes as giving the answers to those questions. And we talk about the instances. For whatever reason, that tends to be the term used when you talk about the algorithms for building decision trees. We talk about the data as having instances of the problem of the task that we're set. We've already talked about data being in tables, so what you want to think about is the questions being asked. That, in our case, maps onto the attributes from the data in tables. So those columns that are each a separate attribute, those are the things that could become questions when we build the decision tree. So the fur type or the personality type, those are each a separate column in our table, and that's what we want to put into the tree. The possible answers are the specified values for the attribute. So up here, we had fur type being short and long. Fur type is one of our attributes, it's one of our columns, and short and long describe that's the only two values that particular column can hold. If you have numeric data, you can work with that in a decision tree, often by dividing it into ranges. So suppose that fur type was actually like measured in centimeters. We could have hairless to very little, where it's like maybe no more than 1 or 2 millimeters of hair, and another that's short-haired dog, where maybe it goes from 2 millimeters up to 2 centimeters, and so on. So you can, in fact, there are algorithms for building decision trees that work well with numeric data by doing something like that, dividing it into ranges. Okay, so we have the possible answers for a particular question. Those are the values that go into the columns of the attribute being the column. And we have the rows of the table being the instances. All of that relates directly to notation from probability, because what we are building is in some sense a probabilistic model of what it is that these instances capture, of the patterns that are there, of the underlying reasoning that's happening. So the attributes and the questions asked kind of correspond to random variables, and the possible values are the values that the random variable can take on. And in that context, then the instances, the rows of our table, the specific instances are the samples that are giving us some insight into the space that we're trying to capture with random variables and probabilities. So these are all talking about the same thing, just with really different terminology. And you might kind of have to bring in your knowledge from different fields in order to get a really rich understanding of what's going on. All right, we're going to stop there. This just gives you a sense of what a decision tree is all about. We're going to jump into how to build efficient, effective decision trees by looking at one of the classic examples, the ID3 algorithm, in our next video. And until then, I hope you're well, and I will see you very soon.